Hi, thanks for joining me today. I'm going to be looking at this problem here, the Putnam 2009 B1 question. It says that for any positive rational number q, there exist primes p1 up to pn, which aren't necessarily distinct, such that q equals p1 factorial times p2 factorial all the way up to pr factorial, divided by pr plus 1 factorial all the way up to pn factorial. So they give us an example, 10 divided by 9, which is obviously a positive rational number. We can write it as 5 factorial times 2 factorial, all divided by 3 factorial times 3 factorial times 3 factorial. And you can verify that. Okay? So the problem actually was stated slightly differently, but this way is an equivalent stating. What I'd recommend is pause the video now and try and have a go at this, and then come back in just a second and I will go through a solution for you. Just going to rub this out. Okay, hopefully you've had a chance to have a go at the problem. What I'm going to do is solve it in a way which I think is quite nice. Perhaps there are other solutions as well, and if you do have any more, let me know. First thing to notice is we're looking at quotients, i.e. the rational numbers, quotients of integers, or positive whole numbers, in fact, because we're looking at positive numbers, positive rational numbers, and the form we want is quotients of prime, of the factorials of primes. So, in fact, hopefully, if you just think about this enough, if you take the quotient of two positive whole numbers, if we can write both of them in this form of quotients of factorials of primes, when we take the quotient of two positive whole numbers, that will also be of the form, and hence any positive rational number is of the desired form. Okay, so let me give you an example to make myself a little bit clear. 3, that's the same as 3 factorial over 2 factorial. Okay, 3 factorial is 6, 2 factorial is 2, 6 divided by 2 is 3. And 7 factorial, that's the same as, 7 is the same as 7 factorial over 3 factorial times 5 factorial. Again, also should note that these are all of the desired form, prime, 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 prime. Okay? Now we can see that 3 divided by 7 is 3 factorial over 2 factorial, and that's divided by 7 factorial divided by 3 factorial times 5 factorial. Okay? And then we can just clean this up a bit. That's 3 factorial times 3 factorial times 5 factorial all over 2 factorial times 7 factorial. Okay? So this illustrates that if we can prove the statement, it's not for positive rational numbers, but just positive integers, we can use that to get any positive rational number. So we've simplified the problem a lot. We now only have to work with the positive integers. Okay? So let's prove that. So we want to prove that any positive integer you give me, I can write in this form of the quotients of factorials of primes. Okay? So we see for the very small numbers, so 1, you can write that as 2 factorial over 2 factorial, for example. 2, well that's 2 factorial times 1, or we can write 1 as 2 factorial times 2 factorial. So this is just 2 factorial times 2 factorial, all over 2 factorial. So again, we can write it in this desired form. 3 is equal to 3 factorial over 2 factorial. Again, 3 and 2 are prime, so that's done. So it's quite easy in the small cases, but you know, if I gave you 127, it's not particularly clear how you would go about finding these prime numbers such that when you take their factorials and take their quotients, you get 127. Okay? But we can prove it in the small cases, so perhaps there's a way we can go and use that information and extrapolate and prove for big numbers like 127 and beyond. And the way we do that is proof by induction. Okay? So we've already shown that it's true for 1 and 2 and 3. We want to show that it's true for all positive natural numbers. So suppose it's true for some number k. Okay, so suppose, let k be a positive integer. Well then we can assume it's true for k. So there exist primes p1, pr plus 1, all up to pn primes. And again, they're not necessarily distinct, such that k equals p1 factorial, pr factorial, all over pr plus 1 factorial, pn factorial. Okay? Now we want to show that the statement is true, or we can find these primes for the case k plus 1. Okay? Well, k plus 1. If you bring your mind back to what we did before with 3, 3 we wrote is 3 factorial over 2 factorial. Okay, and in fact we can do that for any numbers. So t, where t is a positive integer, is equal to t factorial over t minus 1 factorial. Okay, and just to see this, t factorial, that's the same as t times t minus 1 times dot 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 all the way up to 1. But this thing here is just t minus 1 factorial. So this is t times t minus 1 factorial all over t minus 1 factorial. So these cancel and you're left with t. Okay. So any number can be written like this. So we can write k plus 1 as k plus 1 factorial over k factorial. Now, if k plus 1 is prime, then this thing here is a prime factorial, and then we're dividing by k factorial. But then we can just use this thing here, and this thing here is just k plus 1 factorial times 1 divided by k factorial, which is the reciprocal of this, factorial. I should say we should be doing this for strong induction, by strong induction, sorry. So that's important, I should have mentioned that. But so we've shown it's true for k, but we should also assume it's true for 1, 2, 3, all the way up to k. Okay, so then this thing here is k plus 1 factorial times k, over k times k minus 1 times dot dot dot, all the way up to 1. Now each of these numbers here, by the strong induction assumption, each of these we can write as this quotient of prime. So we're going to get a quotient of prime factorials, sorry. So this thing here is going to be a quotient of prime factorials, this thing here, a quotient of prime factorials. There's going to be a bunch of prime numbers factorialed, don't know if that's a word, and then we're looking at their reciprocals, and of course k plus 1 factorial is a prime number. Well, if k plus 1 is prime, then k plus 1 factorial is a prime factorial. So all of this here is just going to be a bunch of primes factorial, and then we can bring them up to the numerator and that sort of thing. But we're going to end up with prime numbers factorial divided by prime factorial, so we're good. But obviously this is the case when k plus 1 is prime. So now suppose k plus 1 is not prime. Well then there must be some numbers a and b, such that k equals ab. And where a and b are positive whole numbers and a and b are less than k plus 1. Okay, and then we just do the same thing. We know that a and b, by our strong induction assumption, these two things here can be written as the product of primes, the quotient of prime factorials, this weird desired form, and then just joining them the two together, we get k plus 1. So if, for example, if we have a equals p1 factorial to pr factorial all over pr plus 1 factorial. I'm gonna rub out this line because we're not just assuming true for kz. It's strong induction, so we're assuming true for all numbers up to k. Anyway, so suppose k plus 1 is a times b, but a, by our strong induction assumption, can be written in this weird form, and so can b. So I know p1 tilde factorial all the way up to pr tilde factorial, pr plus 1 factorial, and I've just put the tildes in just to show that firstly they're not necessarily the same primes, and also it's not necessarily, we don't necessarily have the same numbers of primes on the numerator and the denominator, but yeah, that's just a technicality. And then if I just do AB, k plus 1 is AB, let me put it up here, k plus 1 is AB, and that is just these two products here. So p1 factorial all the way up to pr factorial times p1 tilde factorial all the way up to pr tilde factorial, my pen's running out, all divided by pr plus 1 factorial pn factorial times p1 tilde factorial, pr tilde plus 1 factorial all the way up to p tilde n tilde factorial. So we've shown it's true in the case for k plus 1, provided it's true for 1, 2, 3, all the way up to k. And that's the argument done. We have shown that it's true for the first case, and in fact shown it was true for 1, 2, and 3. And then we showed, well, if it's true for all the numbers up 1 through k, it's also true for k plus 1 by considering the two cases, k plus 1 is prime or k plus 1 is not prime. And yeah, and then it follows from strong induction. And that is your answer done. That's the end of the video. If you did enjoy the maths in this video, please do consider subscribing. It's free, it helps me out a lot, and it lets me know if you enjoy these sorts of videos. But for now I'm done. Have a great day. See you later.